Hello. So, in the last class, what we have done is we have determined a probability that the hidden Markov model is in a particular state, say omega I, at time step t after generating first t number of visible symbols from the given sequence of visible symbols V t. So, for doing that, what we have done is we have defined a term alpha j t, where we have said that initially alpha j t will be equal to 0 if the model is in time step t equal to 0 and this j is not an initial state. Whereas, if we are in initial state at time step t equal to 0, then this alpha j t will be equal to 1 and otherwise alpha j t will be given by this particular expression, that is sum of alpha I t minus 1 into a I j times b j k v t. So, this actually tells you that what is the transition probability from all the states at the previous time step t minus 1. So, that multiplied by the transition probability or emission probability of the tth symbol from state omega j. So, that is what is alpha j t. And we had also written an algorithm which we have termed as forward algorithm to find out the value of this alpha j t, and alpha j t when the machine reaches the final state omega naught, that is what is the probability that the machine theta or hidden Markov theta model theta has generated the given sequence V t. So, let us slightly elaborate on this particular concept. What does this alpha j t mean? Suppose the given V t, so let us take that we have a sequence of 5 symbols and this sequence of 5 symbols are nothing but say V 3, V 1, V 2, V 1 and the final one, as we said, has to be V 0. Okay. So, this is the sequence of symbols V 5 that we have. And if we want to find out the term say alpha 3, alpha 3 at t equal to 3. This says what is the probability that the machine or the hidden Markov model will be in state omega 3 and it will be in state omega 3 after generation of first 3 symbols, that is V 3, V 1, V 2. So, this after generating first 3 symbols, what is the probability that the machine will be in state omega 3. Similarly, if I say what is alpha 2 4, this says what is the probability that the machine will be in the hidden state omega 2 after generating first 4 symbols, that is it has already generated V 3, V 1, V 2 and V 1. So, these are the symbols, sequence of symbols which have already been generated, and after generation of these 4 symbols, what is the probability that the machine will be in state omega 2. Similarly, alpha 1 4, this will specify, this will actually indicate that after generating these 4 symbols, what is the probability that the machine will be in state omega 1. Okay. So, this is what this alpha j t means. So, this alpha j t means that after generating first t number of symbols, what is the probability that the machine will be in state omega j. Okay. So, let us elaborate on this with the help of an example. So, you consider an example. Okay. So, first what I have to specify is I have to specify the model theta, right. And to specify the model theta, we have said that we have to have what are the hidden states, what are the visible symbols or visible states, and what are the state transition probability tables, that is A I j and B j k. So, I assume that the machine has let us say 4 hidden states including the final state. So, I will have omega 1, omega 2, omega 3 and the final state which is omega 0. Let me write it in a different color. So, omega 0 is the final state, and in addition to this final state, it has 3 more states omega 1, omega 2 and omega 3, and all these are hidden states. And at the same time, I also have to have the transition probabilities for the visible states or visible symbols. And for that, let me assume that there are 4 different visible symbols, which are V 1, V 2, V 3 and V 4. So, these are the hidden states and these are the visible states. And in addition to these visible states, we also said that when the machine is in hidden state omega 0, which is the final state or absorbing state, in that state the machine emits only one visible state. Okay. So, that particular visible state, let us say that it is V 0. So, these are the visible states that I have V 0, V 1, V 2, V 3 and V 4. And we also have the transition probabilities. So, the transition probabilities A I j. So, let me assume that the A I j is specified as 1, 0, 0, 0, then say 0.2, 0.3, 0.1, 0.4, 0.2, 0.5, 0.2, 0.1, 0.7, 0.1, 0.1 and 0.1. So, these are the transition probabilities among the hidden states, and similarly I have to have the transition probabilities for the visible states, which actually we said that it is the emission probability, that is B j k. So, I write B j k, which will be given by say 1, 0, 0, 0, 0, 0, 0.3, 0.4, 0.1, 0.2, then 0, okay. So, these are the two different transition probability tables. The first one is the transition probability table or AIJ as shown over here. This is the transition probability table for the hidden states, and BJK, which is shown over here, this indicates the transition probability table for the visible states. And you find that both these tables are indexed from 0. So, this is for omega 0, omega 1, omega 2 and omega 3. Similarly, the rows are omega 0, omega 1, omega 2 and omega 3. Similarly, for BJK, this is for V0, V1, V2, V3, V4 and this is omega 0, omega 1, omega 2 and omega 3. So, as we said earlier that once the machine enters the final state omega 0, it remains in omega 0 only, it cannot come out of omega 0. So, here you find that once it is in omega 0, A 0 0 is equal to 1, but A 0 1 is 0, A 0 2 is 0, A 0 3 is 0. That means, once the machine is in state omega 0, it will always remain in omega 0. The transition probability to omega 0 is equal to 1. Transition probability to any other state is 0. So, which indicates that from omega 0, the machine cannot make a transition to any state other than omega 0. So, it will remain in the accepting state only. Similarly, if you look at this transition table, which is actually the symbol emission table, in omega 0, here it says that B 0 0 is equal to 1, that is in state omega 0, the machine will only emit symbol V 0, it will not emit any other symbol. Whereas, from any other state, there is a finite probability that machine can emit any of the symbols except V 0. Say omega 1 0 is equal to 0, that indicates that from state omega 1, the machine cannot emit the visible symbol V 0. V 0 will only be emitted from omega 0 and this is the only symbol that is emitted from omega 0. And we had also put two more constants. We had said that sum of A I j has to be equal to 1 when you take the summation over j. So, here you find that if you take the sum of any of the rows, the sum will be equal to 1 and this is true for all I. That means, for all the rows this has to be true. Sum of the transition probabilities in a particular row is always equal to 1. Similarly, the other constant that we said that sum of B j k, when you take the summation over k, that will be equal to 1 and this is true for all j. So, here also you find that if you take the sum of all the elements in any of the rows, that is also equal to 1. So, these are the restrictions on these transition probabilities that we have to have. Okay. Now, given this transition probability, my problem is I want to find out that if we are given a sequence of visible states, what is the probability that that sequence of visible states is actually generated by this model theta. Okay. So, for that, let me take a sequence of visible states. Say we have a sequence of 4 visible states V 4, which is given by V 1, V 3, V 2 and V 0. Okay. And as we said that we have to have an initial state, we assume that the machine is initially at t equal to 0, the machine is in one of the hidden states. So, I assume that at t equal to 0, the machine is in state omega 1. Okay. So, this is my assumption, and based on this I have to find out what is P V 4 given theta, where this theta is specified by the set of hidden states, the set of visible states, the transition probability tables Aij and Bjk. Okay. So, this part is Aij. Let me just have a demarcation between these two. So, this is Aij and this is Bjk. So, these four quantities, they specify my model theta. So, what I have to find out is that given this sequence of visible states, what is the probability that that machine theta has generated this sequence of visible states. So, this is what I have to find out, and that is what is my evaluation problem. So, in order to solve this problem, let us have a diagram which is called trellis diagram. So, at different instants of time, so I put t in this direction at t equal to 0, t equal to 1, t equal to 2, t equal to 3 and t equal to 4. At t equal to 1, I have different states, t equal to 0, I have different states. This is omega 0, omega 1, omega 2 and omega 3. So, let me put omega 0 in the first row, omega 1 in the second row, omega 2 in the third and omega 3 in the fourth row. So, this is the situation that I have. And as we said that at t equal to 0, we have assumed that the machine is in state omega 1. So, naturally alpha 1 0, alpha 1 0, that has to be equal to 1 as per our definition, because we have defined this alpha in that form. If you come to this definition, at t equal to 0, if j is initial state, then alpha j t is equal to 1. If it is not an initial state at t equal to 0, then alpha j t is equal to 0. So, just going by this definition, as I have assumed that at t equal to 0, the machine is in state omega 1. So, I have alpha 1 0 that is equal to 1, alpha 0 0 will be equal to 0, alpha 2 0 will be 0, alpha 3 0 will be 0. So, this is the initialization, initial states that I have. Now, let us see what happens at time step t equal to 2. So, here again I have all these 4 different states. Okay. Now, find that coming to state omega 0, I have various possible paths. Okay. I can have a transition from omega 1 to omega 0, I can have a transition from omega 2 to omega 0, I can have a transition from omega 3 to omega 0. Okay. So, if I do this transition, then as we said over here that alpha 1 0 at time step 0, what is the value of alpha 1, that will be given by this expression. And in this expression, I have multiplied by this transition probability, where this transition probability is dictated by V 1. And what is the value of V 1? If you look at this B j k V 1, if you look at this and look at the transition, the sequence of symbols that I have, at time step t 1, the visible state is V 1. And if you look at this, this is my hidden state 0, and the probability of emission of V 1 in state 0 in state omega 0 is equal to 0. Okay. So, whatever path I choose, the probability that this state will exist the existence of this state will have certain probability at time step t equal to 1, that is equal to 0. Okay. So, as I am using this color, let me use this color. So, that is equal to 0, right. Then let us come to this omega 1. You find that I have various ways in which I can have a transition to state omega 1. I can have a transition to state omega 1. From omega 0, I cannot have a transition, because this transition probability is equal to 0. Omega 0, omega 1, this is equal to 0. So, I cannot have a transition to state omega 1 from omega 0. I can only have transition to omega from omega 1 to omega 1. I can have transition from omega 2 to omega 1. I can have transition from omega 3 to omega 1. Right. Now, this transition probability from omega 1 to omega 1, if you look at this, that is equal to 0.3 multiplied by what is the probability that in state omega 1 at time step 1, it will output a symbol which is V 1, because my first symbol is V 1. So, the probability that from state omega 1, it outputs a symbol V 1 is equal to 0.3, right. So, over here it will be 0.3, that is the transition probability from omega 1 to omega 1 multiplied by 0.3 again, which is the emission probability of the visible symbol V 1 from state omega 1. So, this is 0.3 into 0.3. If you come from here, this probability is 0. So, the contribution to this will be 0, this probability is 0. So, the contribution to this will be equal to 0. So, this alpha 1 1, the value of this will be 0.09. In the same manner, here what I have to have is omega 1 a 1 2, that is the transition probability from omega 1 to omega 2, a 2 to a 3 2. Now, the contribution of these two to this will be equal to 0, because alpha 2 alpha 0 2 is 0, alpha 0 3 is 0. So, the contribution from this to this is 0. I will have only contribution from here to here. And this again, if you look at this one, the transition probability from omega 1 to omega 2, omega 1 to omega 2, that is 0.1, and the emission probability of V 1 from omega 2, V 1 from omega 2, that is also 0.1. Okay. So, this contribution will be 0.1 into 0.1, which is nothing but 0.01. In the same manner, I can compute that this will be 0.2. So, these figures in this circle says that this is the probability that my model will be in hidden state omega 1 at t equal to 1 after emitting the first symbol, which is V 1. Okay. And if you continue like this at different time steps, so I will have omega 0, omega 1, omega 2, omega 3, time step 3, omega 0, omega 1, omega 2, omega 3, this is also omega 0, omega 1, omega 2, omega 3. If I continue in the same manner, you will find that here also in time step 2, alpha 0 will be equal to 0. In time step 2, alpha 1 will be equal to 0.0052. You can do this computation. This is nothing but this transition probability multiplied by this multiplied by bjk vt, and in this case bjk is nothing but bj or b1 and my symbol is V3. So, this will be BJ3 or B13. So, this probability multiplied by A11 multiplied by B13 plus this probability 0.01 multiplied by A21 multiplied by V13. Similarly, from here. So, if I add all these different terms, what I get is 0.0052. If you compute in the same manner, here it will be 0.0343, here it will be 0.0057. So, over here what I get is alpha 2 at time step 2 for all j. This is for j equal to 0, this is for j equal to 1, j equal to 2, j equal to 3. This gives alpha 1 for all j. Okay. In the same manner, if you compute at t equal to 3, so here I have alpha j 3. For j equal to 0, I get this. For j equal to 1, I get this. For j equal to 2, I get this. For j equal to 3, I get this. Okay. So, here again this term will be equal to 0. This figure will be 0.0019. This will be 0.0008 and here it will be 0.0012. Coming over here, alpha j 4, if you compute, this will be 0.00138, this will be 0, this will be 0, this will be 0. Okay. And you find that now if you look at this algorithm, the forward algorithm that we had written, the final probability that the machine theta has generated this sequence Vt is given by alpha 0 t. That was my algorithm. And here alpha 0 t is nothing but 0.00138. So, the probability that our machine that we have considered here has generated the given V4, that is this sequence for the given machine or hidden Markov model theta, where this Markov model theta is defined by these parameters, is equal to 0.00138. Okay. So, this is the probability that our given model theta has generated that given sequence. And here at every step, the term the figure within the circle indicates the probability that the model will be in omega 2. So, here in omega 2 at time step 2 after generating V 1 and V 3 as per this sequence. So, it has generated V 1 and V 3. After generating this, the first two symbols, the probability that the machine will be in state omega 2 is given by this. Similarly, after generating these two symbols V 1 and V 3, the probability that the machine will be in state omega 1 is given by this, which is 0.0052. Okay. So, here what you are getting is what is the probability that the machine has generated this V 4, the model theta has generated this V 4, and this generation may be by any of the paths. Okay. Because when computing these probabilities at every time step, I have considered the contribution from all the paths. So, this is the probability that this V 4 has been generated by machine theta, by this model theta, and while generation of this V 4, the model may use any of these paths. So, this is what we said is our evaluation problem. Okay. The second problem that we have said is the decoding problem, and what we have said in the decoding problem is that what is the most likely sequence or most probable sequence of hidden states through which the machine have transited while generating that VT. And if I try to find out this most probable sequence of hidden states through which the machine has made transitions while generating VT, I can simply say that at every time step, I can only consider that state which is most probable. Because you come over here, the most probable state where the machine can be, in which the machine can be at t equal to 1 is 0.2, because the probability that machine will be in state omega 3 after generating the first symbol is 0.2, whereas the same probability for other states is less than 0.2. Okay. So, I can say that in time step 1, this is the most probable state. Similarly, in time step 2 at t equal to 2, the most probable state in which the machine can exist is omega 2, because here the probability that the machine will be in state omega 2 after generating first two symbols is 0.0343, whereas for omega 1 it is 0.0052, for omega 3 it is 0.0057, for omega 0 it is equal to 0. Obviously, here we cannot reach. Okay. So, this is the next most probable state after generating the first two symbols. Similarly, over here the next probable state after generating the first three symbols is this, and obviously, the final state in the sequence is the absorbing state or the final state, which is omega 0. So, once I have this Taylor's diagram, the decoding problem is very, very simple. Okay. I know my initial state was omega 1. So, the sequence of states through which the machine transits while generating this sequence V 4 is equal to V 1, V 3, V 2 and V 0 is the sequence of states omega 3, omega 2, omega 1 and omega 0. So, this is the most probable sequence of states, and that is what is my decoding problem. And once from the Taylor's diagram, I have this simple method to find out to solve the decoding problem. I can also write an algorithm for this decoding problem, and this algorithm is very simple. That straightway comes from this diagram. Okay. So, the decoding problem, we said that given V t, find the most probable sequence of states. Right. So, this is what was my decoding problem. That was the second issue in our hidden Markov model. And obviously, I can write an algorithm for doing this. So, in algorithm, basically what I am trying to do is I am trying to find out the path, the most probable path, which is nothing but the sequence of hidden states through which the model will make transitions. Okay. So, I will have as before an initialization step. In initialization, I set path to be an empty set, okay, and I initialize t to 0. And then I will have a number of iterations. So, I set go for iterations with increment in t and increment in an index j. Okay. Then for j to j plus 1, I put alpha j t will get b j k v t into sum of alpha I t minus 1 times a I j, I going from 1 to n, as n is the total number of hidden states that I have, and this will continue until j becomes equal to C, let us say the number of not C, j is equal to n, where n is the number of hidden states. Okay. And once this condition is reached, then what I have to do is I have to put j hat, which is nothing but I have to find out the state which is having maximum probability. So, this is argument maximum alpha j t, where this maximum has to be computed over j, then append omega j dash to path, and you have to repeat this until t becomes equal to capital T, which is the length of the sequence. And at the end of the algorithm, what we have to do is we have to return the path. Okay. So, if you run this algorithm for this given problem, you will find that you will come out with this path only. Okay. So, this is what is known as the decoding problem, that is, I find out the most probable sequence of hidden states through which the machine makes a transition while generating the sequence of the visible symbols V t. And at the end, what we get is what is the probability that the given sequence of visible symbols have been generated by the given machine theta, where theta is actually specified by the set of states, the set of visible states and the set of hidden states, along with two transition probability tables, probability transition tables. One is the transition probability from the hidden state to the hidden state, and the other one is the transition probability from hidden state to the visible state. And this is not really a transition. What we can call is that this is a probability of emission of visible states from different hidden states. So, these four quantities define my model theta, and given this model theta and given a sequence of visible symbols, I want to find out what is the probability that the model theta has generated this sequence of visible symbols V t. Okay. Now, my final goal is I want to classify this sequence of visible symbols. Okay. So, now you can recollect that when we talked about the Bayes rule, we have said that we have class conditional probability density functions. Okay. That is, what we had is something like P of x given omega I. This was the class conditional probability density function what can be estimated. Now, from an unknown sample say x, to classify this into one of the classes, what we needed to compute is P of omega I given x. And that particular I for which P of omega I given x is maximum, this unknown sample was classified to that particular class. And we have said in that case that what Bayes theory says is it computes, this P of omega I given x is called a posteriori probability, P of omega I given x is called a posteriori probability, and P of x given omega I is called a priori probability, is the class conditional probability. And along with that, we can have an a priori probability. What is the probability of occurrence of a particular class? And we can combine this class conditional probability density function with a priori probability by using the Bayes rule, Bayes theory, which says that P of omega I given x is nothing but P of x given omega I into a priori probability P of omega I upon P of x. So, if I have two classes and the same unknown sample x, I will compute P of omega I given x. I will also compute for another class omega j P of omega j given x. So, these are two a posteriori probabilities. And if P of omega I given x is greater than P of omega j given x, then we conclude that x belongs to class omega I. So, this is what we have done with Bayes classification. Okay. In the same manner, in this particular example or in this particular case of hidden Markov model with a sequence of visible symbols, what we are finding out is P of V t given theta. That is, what is the probability that V t has been generated by theta. But what we need for classification purpose is P of theta given V t. That is, given this visible sequence, what is the probability that this sequence belongs to class theta. So, here again we can apply this Bayes rule. So, this Bayes rule can simply be applied as P of theta given V t to be taken as P of V t given theta, which is nothing but this quantity, multiplied by P of theta, which is the a priori probability, upon probability of this sequence V t irrespective of the models. And once we have this quantity P of theta given V t, then I can use this quantity for classification. So, if I have two models, one model is theta I, the other model is theta j, I can compute this term for theta I can compute this term for theta j, I can compute this p theta I, p theta j, which are the a priori probabilities, and then I have this posteriori probability P of theta I given V t. I also have a posteriori probability P of theta j given V t, and if P of theta I given V t is greater than P of theta j given theta j given V t, then obviously my interpretation will be that V t belongs to class theta I. Okay. So, this is how I can classify a sequence, a time sequence of visible symbols. So, this will be my classification rule. Okay. So, out of the three major issues that we have said, the three central issues in a hidden Markov model, what are the issues we have said? We have said that first issue is the evaluation, where we try to compute what is the probability that a model has generated a given visible sequence. The second issue was decoding issue, where we have found out what is the most probable sequence of hidden states through which the model has made transitions to generate the given sequence of visible symbols. And the third central issue, which is a very, very important issue, is learning of the hidden Markov model or training of the hidden Markov model. And again, as we discussed before, when we talked about the supervised learning and unsupervised learning, when you try to train the hidden Markov model, you make use of a number of sequences of visible symbols, and you already know to what is that visible sequence. Okay. So, as using a number of known visible sequences, you try to train the hidden Markov model. So, the training or learning process of the hidden Markov model is actually a supervised learning. So, now what we try to discuss is learning of hidden Markov model. Which, as we said, it is a very, very important issue. Okay. So, before learning, what we said is the hidden Markov model is coarsely specified. That is, I have a very coarse representation of the hidden Markov model in terms of I know what is the number of hidden states of this hidden Markov model, and I know what are the visible symbols which are generated by this hidden Markov model. So, these are the two quantities which are known, that is the hidden states and the visible states or visible symbols. So, by learning of a hidden Markov model or by training a hidden Markov model, what we usually mean is that we have to estimate the transition probabilities A I j and B j k. So, I know what are the hidden states, I know what are the visible states. What I have to estimate is the transition probabilities A I j and B j k. So, these are the two parameters of the hidden Markov model which needs to be estimated through the learning process. And for estimation of this A I j and B j k, as we said that this is a supervised learning or supervised training process. So, we make use of a number of known sequences, the sequences for which we know that to which of the class those sequences belong. Okay. So, using this we go for training of the hidden Markov model. Now, you remember that when I talked about this forward algorithm, this one, that time we said that for training of the hidden Markov model or for learning, we use a similar algorithm which is a backward algorithm. So, in case of forward algorithm, we have said that this alpha j t, this actually tells you that what is the probability that the model will be in state omega j at time step t after generating first t number of visible symbols in the given sequence of visible symbols V t. When I go for backward algorithm, the backward algorithm says that what is the probability that the machine or the model will be in state omega j at time instant t and will generate the remaining part of the set of the sequence of visible symbols. Okay. So, what I mean to say is that if I have a set of visible symbols which are given like this V 1, V 3, V 1, V 5, V 7, V 2, V 0. Suppose this is the sequence of visible symbols. So, alpha say 3, 4. This gives me what is the probability that the machine will be in state omega 3 after generating V1, V3, V1 and V4 up to this. So, the machine has generated these symbols in the given sequence, and then what is the probability that it will be in the hidden state alpha in the hidden state omega 3. Whereas, if I write say beta 3, 4, what it will say is what is the probability that the machine will be in state omega 3 and it will generate the remaining 4 symbols of the given sequence. That means, it will generate V7, it will generate V2, it will generate V1 and of course, as I said 4, so V5. So, what is the probability that at this time the machine will be in state omega 3 and it will generate V7, V2, V1. Okay. So, in other words, what I can say is that this beta jt or say beta it, this actually represents the probability that model Okay. So, this beta it tells you what is the probability that the model will be in state omega I at time step t and it will generate remainder of the given target sequence Vt. That means, it will generate all the visible symbols from Vt plus 1 to Vt. So, all the symbols from Vt plus 1 to Vt that will be generated and the machine is in state omega I at time state t. So, that is what is BIT. So, in the forward algorithm, we find out what is the probability that the machine is in state omega I after generating first t number of symbols, and beta it in the backward algorithm that tells you that what is the probability that the machine is in state omega I and it will generate the remaining part of the symbols of the target sequence. So, accordingly, I can write the definition, I can define this beta it. So, this beta it will be equal to 0 if omega it is not equal to omega 0 and t is equal to the last symbol. I mean the last time step, that is t equal to t, because as we said that the last state hidden state has to be omega 0 in which the machine generates the only visible symbol which is V0. So, if this condition is not true, then beta it will be equal to 0 and the beta it will be equal to 1 if omega it is the final state of the absorbing state omega naught and t is equal to capital T. In all other cases, this beta it will be sum of beta j t plus 1 into a I j into b j k v t, t plus 1 otherwise, where the summation has to be taken over all j. So, this is the definition of beta jt. Now, if you look at the same diagram that we have used earlier, we can explain that what this actually means. Okay, coming over here. In case of forward algorithm, we have taken all possible transitions from the states in time step t minus 1. In case of backward algorithm, on the other hand, what we will do is, for every state in step t, I will find out that what are the possible transitions to different states in step t plus 1, because all these transitions are supporting the existence of this particular, or the probability of existence of this particular state. So, that is what is done in the backward algorithm, and for that this beta it has been defined. So, as we define this, we can also write an algorithm, this backward algorithm, which we will term as HMM backward. Okay. So, earlier we have written HMM forward algorithm. So, now I write HMM backward. Okay. So, here again we have to initialize, we have to have an initialization stage where I put beta j t, t a I j, b j k and v t. So, all these are initialized. Then we have to have a for loop for t to t minus 1, beta I t will be simply that expression beta j t plus 1 a I j b j k v t, take the summation over j, and this has to be, as we are moving backwards. So, I have to move from capital T to 1. So, until t is equal to 1, and at the end you return p v t, which is beta I 0, okay, for the known initial state. And end of the algorithm. Okay. So, we can estimate the probability that the machine will be in state, say omega I or omega j at a time step t after generating the first t number of sequence, or it will be in the same state at time step t and will generate the remaining symbols from the given sequence by this backward algorithm. Okay. So, I will stop here today. In the next class, I will use both this forward algorithm and the backward algorithm for estimation of the model parameters a I j and b j k. Thank you.